We've talked about a few irreversible nucleophiles already. The Grignard reagent, lithium aluminum hydride, these are powerful nucleophiles that absolutely will not go backwards. And we can add one more to that list. An ylide is a compound that has essentially a negatively charged carbon bound to some other atom, phosphorus, sulfur, oxygen, it can be lots of things, that is a positive charge, permanent positive charge. So essentially what we call a Zwitter ion or a Zwitter ion. It's got both a positive and a negative charge full time. And that's a great example of a carbon nucleophile. So anytime I can get a negative charge on carbon, that's cool. Because that lets me make new carbon-carbon bonds. Called the Wittig reaction. Georg Wittig, old German chemist, lived to the ripe old age of 90. Great reaction for making alkenes, and it starts by taking some alkyl bromide and reacting it with triphenylphosphine. So we haven't really looked at phosphines very much, but phosphorus is under nitrogen in the periodic table. It's got a lone pair like oxygen or like nitrogen does. It's a fantastic nucleophile. We can think about this as an SN2 reaction, very quick SN2 reaction, and we end up with this essentially a phosphonium salt. Right? Now, if we treat that with base, these hydrogens are pretty acidic. And so base is going to be able to deprotonate that, and we're going to end up with this ylide, right? So C minus P plus. And you can draw that like a Zwitter ion. You can actually also draw it with a double bond there. You know, phosphorus is below the second row, and so we can actually think about these things violating the octet rule. That's fine. Okay, so this is an example of an ylide. Again, some dipole that has C minus and some heteroatom plus. Now, what happens when we take this ylide and react it with some ketone or aldehyde? Again, ylides are really great carbon nucleophiles, and we've been talking about ketones as electrophiles. So let's do that reaction. Attack, push electrons up, and what we end up with is we end up with this Zwitter ion. But remember, phosphorus can have more than 4 bonds. And this oxygen negative, this minus oxygen is really attracted to that phosphorus. And so we're going to make another bond there. And we'll end up with this weird 4-membered ring that we call a betaene. Now, it turns out that these things aren't very stable. None of them are stable. As soon as we form this 4-membered ring, it's going to break down. But it's going to break down by spitting out a new compound with a phosphorus-oxygen double bond and another molecule with a carbon-carbon double bond. When the betaene breaks down, we end up with a new alkene and this triphenylphosphine oxide, which is just a byproduct that goes away. But this is a new way to make alkenes. So the old ways that we knew to make alkenes involved elimination reactions where something might lose HBr or something like that. But in those cases, we already had the whole carbon skeleton. This is the first synthesis that we've ever seen that makes an alkene by making a carbon-carbon bond, right? We added this piece and that piece together. So this is a convergent synthesis. Convergent synthesis means that instead of adding one atom at a time or one carbon at a time, I can take a big chunk over here and a big chunk over here and connect them in the middle. And it turns out it's a lot more efficient to be able to connect chunks like that than it is to sort of fight the war one carbon at a time. Let's look at beta-carotene synthesis. If you look at beta-carotene, it's pretty symmetrical. And so that gave chemists the idea to start by building both halves of the thing from the same precursor. So this is beta-ionone, and from that we can make both an ylide and an aldehyde. You can actually make the aldehyde from the ylide too. And so if I take this ylid that we just talked about and I react it with this aldehyde, then I make a new carbon-carbon bond. And sterics, the Wittig reaction isn't very cis-trans sensitive, or it's selective. It can give you both cis and trans sometimes, but for a molecule this size, sterics alone is really going to force it to the trans isomer as being much more thermally stable than the cis isomer. But mixing these two things together gives us beta carotene. Again, I'm making an alkene by synthesizing that carbon-carbon bond. So I'm actually chopping that bond. I don't know if you can see my color change there, but you can almost, thinking backwards, chop that double bond right in half and make it from two different things. So you can imagine that this strategy is a lot more efficient than starting from one end of beta carotene and trying to attach one carbon at a time all the way down the chain, right? So convergent syntheses, and now a new, not just a synthetic tool, but a synthetic paradigm, right? Anytime you see a carbon-carbon double bond, especially if it's a di-substituted or tri-substituted, if there's four things around it, it might be too sterically hindered and congested to get this Wittig reaction to work. But aside from that, anytime you see a carbon-carbon bond, we can kind of mentally chop it in half and say, okay, I can get to this, I can get there from if one of the halves is an aldehyde or ketone and the other one of the halves is this weird phosphonium ylid. But remember, as unique as this looks, we just got there in the last slide from an alkyl bromide, right? You just take an alkyl bromide and react it with triphenylphosphine. So the Wittig reaction, remember it's German, so that W sounds like a V, Wittig reaction. Really nice way to make alkenes.